Okay. All right. So, um, in lesson five, we're going to start diving into different organic reactions for each of the functional groups that we discussed. So, I showed you a bunch of functional groups in the previous video. We're going to go through most of those functional groups' organic reactions. We're going to start with alkanes, then talk about alkyl halides, aka haloalkanes. So, these are sometimes called haloalkanes. Okay. Or alkyl halides, same thing. Then we'll do alkenes and alkynes. Remember, alkanes have CC single bond, alkenes have CC double bonds, and alkynes have CC triple bonds. And alkyl halides essentially have CX bonds, right? So you have halogen or X in the molecule. So I'm going to start with alkanes. So let's start with alkanes reactions. Remember, alkanes all have single um, carbon carbon bonds. When we look at their overall reactions, essentially we see three things. Essentially, we see three things, or we can group them into three categories. The first category are what we call free radical reactions, or free radical halogenation. Okay. And I'm going to explain what that is. But what you're trying to do here is you're trying to halogenate. Remember, halogen is group 7, which is your X. Basically, what you're doing is you're trying to make alkyl halides from alkanes, right? Through free radical uh, halogenation. The second group is pretty simple. You guys have heard of that before. It's called combustion. So essentially, um, when you burn paper, when you burn wood, when you cook food, essentially that's a combustion type reaction. And finally, we have substitution reactions. In this case, you're substituting um, something for something. So maybe you're substituting an alcohol with, I don't know, with an X, right? Or you're going from CBr to COH or something like that. You're replacing or substituting um, one group or one region for another group on the same region. So let's talk about each of these reactions briefly. The first group is free radical substitution. So um, essentially, what you have here is something like alkane, which will give you alkane free radical. Usually, you put a dot on top of your molecule or region or carbon or whatever atom you have to depict basically free radical. A free radical species usually is shown by a dot as shown. To do that, you typically introduce a free radical of halogen or X halogen. Let me just put X. You introduce the reaction, or you introduce the alkane with a free radical. You produce another free radical, and then finally you get alkyl halide. These types of reactions undergo three stages. They undergo initiation, then they undergo what we call propagation, and finally you have termination. Okay, so that's basically free radical reactions for you. Um, when we look at, let me just move this up, down. Combustion reactions should be easy for you guys. You've seen that before. So let's just say I have C3H8. And let's just say you have complete combustion with a plethora, depot of oxygen, plenty of oxygen. So that's complete combustion. In this case, you get 3 carbon dioxide CO2s plus 4 water plus lots of heat, of course, right? I'm going to actually put the heat here. Heat, delta H or enthalpy of these reactions is always positive. Negative, sorry. We will release heat. Okay, so that would be an example of combustion reaction. And finally, substitution. So when we think about substitution, you have to think about, so I'm going to put that down here. You have to really think about different types of species that we use for substitution. So there are species specific for substitution. Okay, so I'm going to talk about that here. Actually, let me just mention something. So when you think about substitution, you have to think about two types of substitution. You have to think about two types of substitution, no, namely SN1, SN2. SN2 reactions, which I'm going to talk about in a second. So, but before we talk about that, you also want to know about nucleophiles, nucleophilicity, basicity, and leaving groups. Now, because we're going to cover this part of organic chemistry in Unit 2, I'm not going to spend too much time on it now. But what I will say is that I will show you guys a chart to compare and contrast these types of reactions. Okay, so let's actually make a chart here. So we're going to discuss, or we're going to compare SN1 reactions with SN2 reactions. So these are SN1 reactions versus SN2 reactions. Remember, S just means, so I'm going to explain what S means. S in both cases, I guess I'll just write that up here. S means substitution. N means nucleophilic. Nucleophilic. Now, 1 and 2 have other meanings, which we'll talk about in a second. Essentially, these are called nucleophilic substitutions. So maybe I should put that up here, actually. Nucleophilic substitutions, or SN reactions. SN reactions. So let's actually see, compare and contrast these two types of reactions. So you can see there's one, there's two here. So let me show you what one here means. One basically means that this is essentially unimolecular. Unimolecular. Two means bimolecular. Bimolecular. You then have the other difference is that the rate of the reaction is defined as K Rx. I'm going to explain these rate formulas in Unit 2, actually Unit 3, I believe. And then this one the rate of the reaction is calculated as K nucleophile and then Rx. Okay. Again, you guys will see what's Rx, you will see what's Nu, you will see what is K in the future, but have this table handy for now. We'll come back to it soon. SN1 reactions, they're favored in what we call polar protic solvents. So they like polar protic solvents. This is despite the fact that these have or like polar non-protic or aprotic solvents. The reason is that the nucleophile, remember nucleo means positive region because nucleus is positively charged, right? Nucleophile comes from philis or philicity or philis or philia, which means you like. Okay, philia or philis or philis means you like something. Phobia means you don't like something. So if you are a nucleophile or nucleophilic, then you like positive centers. Protic, proto comes from proton. It's a positive center. The problem is that if you put something, if you put a SN2 reaction, if you have it happen in a protic solvent, because you have lots of protons, these nucleophiles are going to react with the protons and not the Rx. Rx is your alkyl halide in this case. And you will not get a reaction. Essentially, if you have protons around, you will disrupt the reaction. So that's why these reactions have to be in aprotic solvents. Protic solvents are solvents which have lots of protons or positive charges, as shown. These guys, they don't have the nucleophile involved, so there is no problem to have um, problems. Sorry, to have protons. That's not an issue. The next difference here is that when we look at different types of alkyl halides, I'm going to explain that as well. Just like where we had primary, secondary, tertiary, if you guys remember, alcohol and amines, you kind of have the same thing here, guys. You have, this is methyl. You kind of have the same situation here. You have primary, secondary, tertiary alkyl halides. And if that's the case, you will have to know, you would hopefully have a tertiary alkyl halide as opposed to a primary one, because tertiary ones will like SN1, and in fact, the order will flip when you look at the order will flip when you look at the SN2 reactions. Now, tertiary alkyl halides will be unfavorable for SN2 reactions. In terms of the products that we get, usually when you have SN1 reactions, because the attack can happen from the top and the bottom, um, when the reaction happens, or the nucleophile can attack from the top and the bottom, or from both sides of the stereocenter, that you end up getting racemic mixtures. So here you get racemic products. The products of SN1 reactions typically give you R and S, right? So you would have essentially optically inactive products. Here, the products are optically active, and they are inverted products. Okay. And finally, in terms of which nucleophile should you use uh, for these types of reactions, and the answer here is that you want to have a strong nucleophile not required. So a strong nucleophile not required. It's not needed because remember, this is called the rate law, by the way. In the rate law of SN1, you don't have nucleophile. Okay, so its concentration is irrelevant. You can have high concentration or strong nucleophiles or weak, and it would not make a difference. Here you would have favored with a strong nucleophiles. Okay? All right, so those are some of the basic differences between SN1 and SN2. We will come back to SN1, SN2 reactions later on. So I will in unit 2 or 3, I believe, somewhere in those units. But yeah, I think that's enough of description of alkane reactions. So in summary, you have three types: combustion, free radical, halogenation, and finally we have nucleophilic substitutions. Technically, it's a free radical substitution type reaction here as well. You're substituting a hydrogen with a halogen. Here you're substituting two species. One of them is nucleophile. Leaving group essentially is what leaves the product, or it's what leaves the alkane. So I will tell you a bunch of trends, a few trends here for you to know when you guys see reactions for alkyl halide nucleophilic substitutions. So let's actually do that now. So basicity and nucleophilicity, they are somewhat commensurate. Okay, so when we look at nucleophilicity, when you look at nucleophilicity, you basically have you basically have the following. So remember, R is the same thing as before. It's the same thing as before. Give me a second, guys. Okay. So RO means essentially something like maybe an alcohol that has lost its proton, right? So maybe it was ROH, and you lose a proton, you become RO minus, right? You can also have HO minus. That's a water, which would be deprotonated too. Remember, water can also act as an acid. It can lose its proton, and you can see right away that a what we call OH minus hydroxy group or hydroxide ion is a weaker nucleophile compared to RO. Now you have to understand why that is right away. If you can think about what's happening or why that is, right, it will help you memorize. Remember, this negative charge is going to attack a positive charge, which basically means is that the stronger the electron, um, the stronger um, the stronger the electronegativity next to oxygen, right? The more electron donation you would have, and the more negative charge you will have. And if you have more negative charge, you would attract the positive charge better. Okay, so let me repeat. Negative charge here as a nucleophile is going to want to attack or attach to a positive charge because these are nucleo or positive center philis or philicity, which means they like it. So they like positive centers. If you like positive center, you better have lots of negative electrons or a lot of negative region. In this case, because you have R next to oxygen, remember R is typically carbon, and I'll show you guys next time. Carbon typically donates electron clouds to its surrounding, molecules or atoms. So in that case, this becomes more negatively heavy uh, compared to OH minus. It would make it a better nucleophile. When we look at, or it would also be, you could also argue that this is a stronger base too, right? Here, RO minus is a stronger base than OH minus. The next one on the list is RCO2 minus. Now, RCO2 minus looks like what? Looks like this, correct? This is a carboxylate anion. Remember, this comes from a carboxylic acid region, so this would be as weaker. It would be a weaker base in this case compared to OH minus. So hence it would be weaker than OH minus. Next, we have ROH. Notice how now you've lost the negative charge. There's no longer a negative charge. So this is essentially the same guy here, except now it's protonated. and finally water. What this chart shows you, guys, is that if you look at this trend, you are assessing nucleophilicity based on the basic tendency of the compound. If somebody asks you who is the stronger base, you would say RO minus, and in this case, it would make RO minus the strongest nucleophile. In other words, the trend in basicity matches the trend in nucleophilicity here. So again, the guys on the left are stronger bases and stronger nucleophiles compared to the ones on the right. Next trend would be based on polarity and size. So I'm going to say nucleophilicity, and size / polarity. Now we talked about polarity or polarization, in grade 11. For those of you who remember, I said in grade 11 chemistry that if you are getting bigger, so let's compare A and B. And what I told you before was that if you're a bigger guy and you have a negative charge on you, you would basically become um, uh, you would accommodate the negative charge easier, and the negative charge would be more stable, and it would be why? Because you would have more room to accommodate negative charge. So we talked about size in that sense before. We also said that if you're bigger, so let's say you are A versus B, that B is more polarizable, right? So we talked about that as well. So that B is more polarizable, which means that if you have a bigger molecule, because of the size, you become more polar easier. Okay, so polarizability or the ability to become polar is directly proportional to the size. Smaller molecules cannot be polarized easily. Large molecules can easily be polarized. And if you're polarized easily, if you're bigger, you would expect that you become a better nucleophile too, because in that case, you would have more negative regions around you or more negative polar regions so that you can attack a positive region. Remember, if you're not polar, right? If you cannot be polar because you're too small, then how are you going to attack a positive center? You can't. So the idea here is that if you're bigger, right, you can be more polar, you can be more charged, probably negatively in this case. And in that case, you can attack a nucleophilic, or you could become a nucleophile or attack a positive center. Okay, so let's write down the trend. So Cn minus, that's called cyanide. That's the most strongest nucleophile. It's I minus next. Then you have RO minus. Then you have OH minus. Then you have Br minus. Then you have Cl minus. And you have F minus. Let me just make this a bit smaller. And finally, you have H2O as shown. Okie dokie. So what you're looking at, first of all, if you look at your halogen, so that's your X, that's your group 7. Look at fluorine, chlorine, bromine, and iodine. The guy who is bigger is more polar. It can maintain its negative charge easier, which would make it a better nucleophile, right? And then you have these ones in the middle, which you can just try to memorize. Obviously, if you are not charged, you would become a weaker nucleophile compared to if you are charged, right? So all of these, obviously, ones here are charged except for water. So if you're not charged, obviously you would become a weaker nucleophile. Sometimes when we show nucleophilicity, guys, sometimes we put Nu double per electron minus. Sometimes we put like that. Guys, if you see in the textbooks, if you see Nu for nucleophile, this double dot here represents an excess or extra electron pair. If you're NO minus, you're thinking something like this. You understand? Because you're charged. So sometimes I put Nu minus, sometimes I put Nu with no charge. And most of the time we put Nu minus because those are the stronger nucleophiles. But if you're not charged, such as these two, technically you're supposed to use Nu just dot dot. Okay. And finally, so that's the strength of nucleophile. So when we look at, when you guys trying to see if you need a strong nucleophile or not, you look at this list. Now you can imagine that the ones on the right, sorry, on the left, they would give you SN2 reactions, and the ones on the left will most likely give you SN1 reactions. Why? Because if you are a strong nucleophile, you tend to favor or undergo SN2 reactions. If you're a weak nucleophile, you tend to favor or undergo SN1 reaction. So that's how that works. But it's not just the nucleophile that you have to worry about, it's also the strength of the leaving group. So when you look at leaving groups, when you're assessing leaving groups, what are you trying to look at? Well, first of all, weak bases are best. So weak bases make excellent LGs or leaving groups, okay? So what are some of the examples for a weak base? Ammonia. You guys know this from grade 11. Ammonia is a very nice, very potential prototype, a very good prototype of a weak base, or any sort of amine base, or any NH2 type base. So most amine bases, most amine based bases are weak bases, which would make them really good leaving groups. In terms of trends, I'll write them down here for you. So I minus, let me just put these here. Oh, there we go. And you can see these are all your halogens, right? So there. Make sure you know this trend. So what this means is if your leaving group is I minus, it would become a better leaving group compared to F minus. Oh, I should take this out. Now, if you're wondering why, so this is a different type of description. Okay, so don't try to compare this trend. Don't try to compare this trend with this trend. Okay, you're talking about two different things. This is a leaving group situation. Um, and if you're wondering what's going on, so remember, if a leaving group is what leaves the alkane, and then it gets, and then you replace it with something else, hence substitution. So if you're having, let's say, I don't know, if you're having, so let's say CI, which is trying to become, let's say, C whatever, let's just say C, I'm going to put a circle and then I minus, and here we're just adding a circle, I minus, right? Let's just say this is negative charge. So if this is your nucleophile, and that's your But let's say you're having a nucleotide, you want to replace and substitute the iodine. The question is, if you have iodine versus chlorine, which one would be a better leaving group? And the answer would be iodine. If you had the same reaction and instead of iodine you had bromine, that bromine would happen less favorably than iodine. Iodine reaction would happen easier or with less energy or more favorably. Okay, so that's the lesson for alkanes. Later today or over the weekend, I will send more videos um, about this. Remember, tomorrow we don't have lesson. The lessons will resume technically Wednesday next week. But over the weekend, I'll keep you guys posted with the rest of these lessons to finish because we still have to finish alkyl halides, alkenes, and alkynes. So those lessons will be sent over the weekend, and then I will resume lessons on Wednesday. Have a good weekend, everybody. Talk to you soon.